Hi everyone, welcome back. We are back for the final video of the semester, and this is going to be a review for the final exam. I'm going to keep this video a little bit on the shorter side. I basically just want to give you kind of an overview, like an outline of topics, and just remind you of some of the things that you should be studying. So I'm not planning to do any new problems today or any new material or anything like that. Just kind of a recap, cover some of the highlights, and remind you of what you should be looking at. So the most important thing is that you should be studying on your own. I can't study for you, but I can at least maybe point you in the right direction. Okay, so let's take a look at this. All right, so let's start just by saying the final exam is cumulative. It's going to cover basically every lesson that we've had is fair game for the final exam. In fact, you could actually look at the schedule of topics that we've had and you could kind of use it as a checklist. Um, just look at every section that we've had. Oh, by the way, the date and time are in the syllabus. So that's been there since day one. What I want to tell you is maybe some suggestions for things that you can study from. Suggestions of things you can study from. So, of course, your notes, right? You've been taking good notes all semester. Now's the time to use them, including examples done in class or done in lessons. Anytime that I've had you do a problem in a lesson or anytime I've done a problem for us, those are the problems that I like. So it's good to go back and review all of that. You can study from homework. You can study from quizzes and exams that we've had so far. So on the midterm exams that we've had so far, if you haven't done this already, now is the time to go back and make sure you understand every problem from the exams that we've had. If there was a problem that you got wrong, make sure you understand it now. Also, go back and review the problems that you got correct also, because maybe you remembered, like maybe you knew how to do it back when we had exam one, but it's been a while, so you should still go back and look at those anyway. How about the textbook that we've been following along with and the author's examples, which might not be the same as the examples that I've done, especially for sections that you find tricky, right? Especially if there's a section you find difficult, look very closely in the textbook at it. How about worksheets that we've had? Yeah, we've had a good amount of practice problems in worksheets. So basically study from all of these things. For linear algebra, we're getting more into kind of the mid-level to upper level math courses. And usually at this level, we don't give you a review packet at the end or anything like that. So I don't have like a review packet of problems. You've had problems all semester, and I think there's plenty of them for you to go back and look at. But what I'm going to do now is just kind of cover sort of an outline, some highlights, to remind you of some things that you should be studying. All right, so we started the semester looking at chapter 1, and it began with solving a linear system. In a way, that was kind of our motivation that got this whole course started. Everything started with us trying to solve linear systems, maybe find where do two lines intersect. And then we built on it from there, and we did a lot of things from there, right? We learned about row reduction, which is Gaussian elimination. And we also learned about Gauss-Jordan elimination. We learned about reduced row echelon form, which I'll just write as RREF, reduced row echelon form. That's the result of Gauss-Jordan elimination. We learned about pivot positions and pivot columns. We learned about free variables and basic variables. And we learned about writing a solution set in parametric vector form. And that came up a lot throughout the semester. So remember, when you solve a linear system, there might be one unique solution, or there might be no solutions. That would be if the system is inconsistent. Or there might be infinitely many solutions. And when there's infinitely many solutions, our preferred form of writing them is we write the solution set in parametric vector form. Now, that already would be a good amount of material on solving linear systems, but this chapter also went a bit further, and this is when we talked about linear combinations. Linear independence. You should know the difference between the two of those. And span. You should know what a spanning set is. Like, you should know what the word span means and how it's used. Yeah, so linear combinations, linear independence, and you know what? This chapter also had the introduction to linear transformations. So a lot of material that we've used all semester originated in this first chapter. And we did spend, we spent a pretty good chunk of time on these topics. By the way, what do you need to know about linear transformations? I guess one thing that you should know is you should know how to prove that something is a linear transformation. Like if I give you something and I say, is the following a linear transformation? Why or why not? And prove your answer. Remember that you can prove this using the definition, which has 2 steps, or you can prove it in 1 step by verifying that T of Cu plus dV equals Ct of U plus dt of V. Remember that? That's if something is a linear transformation and you're trying to prove it. You prove this one thing, left-hand side equals right-hand side, and you're done. I guess another thing about linear transformations, I guess I'll say, is also, yeah, I guess this was all in chapter 1, was finding the standard matrix A. This is not necessarily an exhaustive list. There may be other things. How about, is a given transformation one-to-one or onto? Remember, there's a way that you can tell this based on the matrix A, and that's probably how I would do it. So that's kind of an outline for chapter 1. Let's look at chapter 2. Some of these ones are going to be a little shorter. But this is where we started looking at matrix operations. Now, I know that when we talked about matrix operations, we kind of focused on matrix multiplication, but don't forget the other ones also. Like you could do something such as, what if I gave you a matrix A and a matrix B, and I asked you to find like 3A plus 5B? Yeah, that's like scalar multiplication and adding matrices. You could do that. You could do A times B. You could do B times A. You could do A transpose. Those were discussed in that lesson on matrix operations. And then we had a lesson about the inverse. A inverse. And originally we talked about that for the 2x2 case. And then we talked about the 3x3 case and so on. And this led us to the invertible matrix theorem. The invertible matrix theorem, I hope that you can tell that the IMT is a big deal. It's a very big deal for linear algebra. It's a very long theorem. I don't expect you to memorize every statement that's in it. I'm not going to ask you to state the invertible matrix theorem. It's too long. I'm not going to ask you to memorize the whole thing. But you should know the important parts of it. Like you should know which parts of it tend to come up in problems. So, we've answered some questions using the IMT. You could go back to that first lesson on the IMT and see what we answered based on it. And any time that it came up since then. So some of the statements that are in it, I would say, are more important than others. So go back and look at that. Then we moved on to talking about subspaces and bases. All right, so in this lesson, we were talking about subspaces of Rn and, a basis for them. Oh, you could also be asked to prove that something is a subspace. So to prove that something is a subspace, that has 3 steps, right? 3 conditions. You need to know that the 0 vector is in H. I guess I'm calling it H. You need to show that U plus V is in H. You need to show that C times U is also in H. And you should know what I mean. I'm not writing out all of this. C is a scalar, U is an element of H, and so on. Oh, and I guess also H has to be a subset of Rn. The definition of subspace started off by saying if H is a subset of Rn and it has these 3 conditions, then it is a subspace. Speaking of subspaces and bases, that led us to talking about dimension, rank, and nullity. Oh, I guess I should also say some of the popular subspaces or popular examples of subspaces are the column space of A and the null space of A. You should know how to find those. And I guess that means this must have been where we saw the rank nullity theorem. So that's a good outline for chapter 2. Let's see. So we spent a lot of time on chapter 1 and 2. It's a lot of a lot of concepts that are important to linear algebra. Some of the other chapters that we did were a little bit shorter. And what we've tried to do in this course is kind of give you a sampling of different topics. You know, in chapter 1 and 2, you kind of learned the tools that are used in linear algebra. And then we looked at a little bit of chapter 3, 4, 5, and 6, but we didn't really complete those chapters. Anyway, this was about determinants. Now, we had already talked about determinants in chapter 2 for the 2x2 case, but this is for 2x2, 3x3, and larger. And this led us to an important result, which is that the determinant of A is non-zero will imply that A is invertible. And we added this to the invertible matrix theorem. Actually, this is if and only if. We can make it a double-sided arrow. That's for a square matrix A. So sometimes you might be given a problem that's just like, here's a matrix A, and it might say to find the determinant of it, and then it might ask you, is A invertible? And you can answer that without finding the inverse of A. Like if it's just a yes or no question, is A invertible? Sometimes you just say yes, and maybe you have to justify your answer, but you don't necessarily have to find A inverse unless the problem tells you to. Let's see, there was a little bit more in chapter 3. I guess there were some properties of determinants. So go back and look at the properties of determinants also. Chapter 5, we talked about eigenvectors. Oh, I'm sorry, chapter 4. I'm getting ahead of myself here. Chapter 4, we looked at vector spaces besides just Rn. Yeah, so this was a little bit like the lessons that we had earlier on subspaces and bases, except now we were not just restricting ourselves to Rn. So I'll tell you, some examples that we looked at. We had something called Pn, and that was the space of all polynomials of degree at most n. Remember that? So you could have a vector space of objects that are not vectors in the traditional sense. They could be other things like polynomials. Oh, another one that we had was Rm by n. And this was the space of all m by n matrices. So in this vector space, every element is a matrix. I believe we only had one lesson from that chapter, but I think it is an important one. Then we got to chapter 5. Chapter 5 was about eigenvectors, eigenvalues, and eigenspaces. You should know what each one of those means, and you should know how to find them. And for the eigenspace, usually we want to find a basis for each eigenspace, because finding a basis is the best way to describe an eigenspace. In fact, finding a basis is kind of the best way to describe any subspace, because it's all based on that. In our discussion of eigenvectors and eigenvalues and how to find them, that naturally led to us talking about the characteristic polynomial. And I guess we actually had two definitions. We had a definition for characteristic polynomial and a definition for characteristic equation. Well, the characteristic equation is just when you set the polynomial equal to 0. I mean, it has an equal sign, so it's an equation. But yeah, characteristic polynomial is what we use to find lambda, which is the eigenvalues. Some of those problems, they kind of take a while, right? If it's a 2x2 problem or a 3x3 problem with multiple eigenspaces, some of them take a while. You might have to do some factoring of polynomials, things like that. On a final exam, I do try to take into account how long a problem is going to take, but there's still problems that I could ask you around that. And then we looked at diagonalization. Diagonalization is sort of an application of this, and not every matrix is diagonalizable. But if a matrix is diagonalizable, we found how to find the matrices associated with that. All right, then we moved on and looked at a little bit of chapter 6. We didn't do a lot of this, but in chapter 6, we had inner products, length, and orthogonality. Orthogonality is just whether or not two vectors are orthogonal to each other. You should understand that when we drew pictures of that in R2, it seemed like it kind of corresponded to our usual notion of perpendicular. I mean, we're talking about vectors here. We're not talking about lines. But vectors that are orthogonal kind of point in opposite directions. And that's when the inner product is equal to 0. By the way, you should know that some of these things had more than one name. The inner product might be referred to as the dot product, and the length might be referred to as the norm. And we had notation for these. We just did this recently, so I think we should be okay with this. We also talked about the distance between two vectors. So I'll say, and dist u comma v. Oh, also normalization and unit vectors. Normalizing means finding a unit vector that points in the same direction, and in order to do that, you need to find the length of the vector and divide by it. One thing I want to say is, in writing these outlines, I think that you can see that not all of these chapters are weighted evenly, right? Like, we had a lot of material in chapter 1 and a lot of material in chapter 2. And we didn't really do very much with chapter 6, and we didn't really do very much with chapter 4. So when I write the final, I write it kind of proportional to how much time we spent on something. All of these sections could be on the final, but I guess what I'm saying is I would expect more from chapter 1 than chapter 6. That just makes sense, right? Okay, so after chapter 6, we had some extra topics. The things that we talked about recently. We had efficient matrix multiplication. In this we talked about Strawson's algorithm, Lauterman's algorithm, and so on, and some recent progress. And then we talked about an application of linear algebra to 3D graphics, which is really an application of matrix multiplication and linear transformations. So what I want to say about these two extra topics is these two things were not in the textbook. These are lessons that I came up with that I thought would be nice to include. I would like you to know the main concepts. I would like you to be able to describe what is efficient matrix multiplication all about? What is 3D, what is the application to 3D graphics all about? Why does it use 4x4 matrices instead of 3x3? Things like that. I'm not going to ask you to memorize Strawson's algorithm or Lauterman's algorithm, and I'm not going to ask you trivia about what year was Strawson's algorithm or anything like that. It's not about every little detail. It's about, the broad concepts. All right, so this has been an outline of what we've done. Maybe this doesn't include every little detail, so you'll see other things as you go through and study. I guess earlier I mentioned, let's see, I mentioned linear combinations, linear independence, and span. I think that those things kind of came up a few times. Like span came up again when we talked about eigenspaces. Row reduction. So I mentioned row reduction in chapter 1, but really row reduction showed up almost everywhere. We used row reduction sometimes when we were trying to find eigenvectors and eigenvalues. So sometimes I might list something as chapter 1, but really it's used in multiple chapters. All right, I guess that was what I wanted to cover, so we could wrap things up here. So what else can I say? All I really kind of set out to do in this lesson was to just give you an outline of topics and, a quick refresher and reminder of the things that you should be looking at. So you should study for the final exam, and, you can look in the syllabus to see how much of the grade it counts for, but, exams do count for a good portion of the grade. It's an opportunity to pull your grade up or down. It depends how it goes. What else can I say? I think everyone here can do well on the final. I know you can do this. So take it seriously and study for it. Make sure that you have fixed any mistakes that you had in the past. Like if there was something on an exam that you didn't get, make sure that you understand it now. And on the day of the final exam, make sure that you are well rested. Make sure that you have something to eat. Have caffeine if you're the type of person who does caffeine. Whatever works for you. Just you want to be at your best, right, for final exams. You know this. You've been here for a while and you've made it to linear algebra. You know what to do. So I guess that's going to be it from me. So good luck to everyone and take care.